Good luck too.
Cheers.
Hello, good morning, good evening, and good afternoon. My name is Nick Shanley, and welcome to our third webinar from Saft. This one is going to be Saft lithium-ion safety, debunking the risks. It's about a 40-minute presentation followed by a Q&A section. We're going to be discussing things like lithium-ion standards, thermal runaway, ventilation requirements, and today we have two experts speaking. First, Nick Finney. He's our lithium-ion product manager. He has 30 years experience with Saft, 5 years as product manager for the industrial standby division. And second, we have Michael Mallis. He's the certification manager, 3 years with Saft and 8 years experience in the automotive industry. And with that, I will turn it over to Mr. Finney to start our presentation.
So thank you very much, Nick. Welcome, everyone. It's a pleasure to be with you today. Just to give you some context to this debunking, what do we mean by debunking the risks? So often in the news, we see reports of the effects of problems that are experienced, either failures, for example, that are experienced with lithium-ion batteries, whether it's commercial grade that you find in industrial mobile phones or in electrical vehicles, e-cigarettes as well is often reported. And the point here is that often there's a degree of sensationalism. They're trying to sell their newspaper or their news, and often the cause is missed or it's not investigated, and we're left in the public eye with a little bit of anxiety, let's say, about these. You'd be left to think that it was happening every day. So the point of this webinar really is to take our most frequently asked questions that we receive that relates to products and installations, so the real world, and to address these items that we feel may be of value to you today. So let's jump straight in. So the first question is lithium iron phosphate, or LFP, safer than lithium manganese oxide? Well, it's a great starting point. And just to take a big picture view of this, lithium ion is really an umbrella term. And what do we mean by that? So with lithium ion, there's many different dissimilar metal combinations. So when we talk about LCO, lithium cobalt oxide, or nickel cobalt aluminum, or nickel manganese cobalt, for example, these are all referencing to cathode or positive active materials. Often in terms of reactivity or energy power density, this is ordered from the most energy efficient design, the LCO, and we go through our oxide reactions, our oxide materials, and as we come down the list, we decrease the available energy in a battery system, but with that comes an increasing level of safety. So for the purpose of today's webinar, we'll focus mostly on two types of chemistry, what we call LMO, or lithium manganese oxide, and LFP, lithium iron phosphate. And just to take your attention to the curve here, I can pick up a laser. So just to bring your attention, so LMO has a higher nominal voltage per cell of around 3.6, 3.8 volts per cell. And it's quite a steep curve relative to the lithium iron phosphate, the LFP. And so you've got two traces here. The upper voltage, the upper curve is the charge voltage characteristic, and then there's a slight suppression in voltage for during the discharge, and that's the same for the iron phosphate here as well. and we'll come back to these characteristics later on. There's in terms of development as well, we have lithium manganese phosphate that's in the process of being industrialized. This has a very close level of safety to iron phosphate, and the addition of manganese increases the voltage per cell, so we recover the amount of energy and power per cell is closer to an oxide, but with the phosphate safety. The takeaway here is that safety starts with cell chemistry. It's certainly not the be all and end all of safety with lithium-ion systems, but phosphate is considered in the industry as safer than oxides. So we'll just take a couple of slides to look at the two areas of focus, the lithium manganese oxide, the LMO, first of all. It definitely delivers a higher level of safety compared to other oxide combinations such as nickel manganese cobalt or nickel cobalt aluminum. Often LMO is actually an umbrella term itself. It's often a blend. For example, it could be about 70% LMO with about 30% nickel manganese cobalt. Or it could be the other way around, where you have about a third LMO with about 2/3 NMC. But both of these mixtures fall under the description of LMO. Compared to other chemistries, it has a reduced calendar life, especially if you start to operate the battery system in a higher than ambient temperatures above 25 Celsius. The main takeaways on the plus side, we have high cycle life at room temperature, and it's the highest level of safety out of the oxide combinations. The challenges with the chemistry is that we have reduced calendar life once you start to operate it at a higher ambient temperature due to the manganese dissolution, and it has a lower safety than iron phosphate or lithium titanate combinations. If we look a little bit more now at the iron phosphates, it's really the beginning point, the choice of major manufacturers where safety is your driver. If you're in a manned building, for example, you need something that is perhaps more safe and less reactive than other types, because you have life safety to consider as well. It's important to distinguish with LFP between commercial grade and industrial grade products. Commercial grade often in the small cell formats. We're talking about 18650, which is the cell type that's a little bit bigger than AA size, up to about the old C size type designs. These are commercial grade and tend to have shorter calendar life because they tend to be high volume, mechanically crimped caps, rather than having say laser welded caps that we have on large format. And typically, generally we say that if it's below 10 ampere hours, then it falls into the commercial grade product, versus above 10 ampere hours, which is generally more industrial designed. The highlights are that it's the safest amongst the lithium-ion chemistries, excluding those that use lithium titanate in their negative plate in the anode, and it has a very low change in its impedance. So during the course of its life, let's say over 15-20 years, the impedance changes very little, which means that you get a very stable power output throughout the life. So it doesn't drop significantly during the aging of the product. The challenges is that it does have lower energy with the exclusion of titanate compared to oxide materials, and that you remember on the curve that the recharge was very flat. The characteristics for LFP, iron phosphate, and the challenge there is that when you have a low state of charge below, say, 85%, when you're recharging the product, you have to have quite sophisticated electronics in order to precisely measure and manage the balancing and the recharge of the cell. So I'll invite Michael to speak now for FAQ 2.
Good morning, Michael Marie speaking. Question number 2. What's meant by venting, smoking, thermal runaway, explosion, and fire? Most important and used terms for describing the behavior of the cell during thermal abuse testing are venting and thermal runaway. Venting, as you see on the picture on the right, stands for controlled reaction of specifically designed bottom of, for example, cylindrical cell to increased internal pressure due to temperature rise. Cell surface temperature during venting differs with the chemistry which is used. Thermal runaway can follow the venting and is uncontrolled increase of heat from the inside of the cell caused by gradual reactions of the material keeping the energy inside. Explosion and fire, these terms are quite clear. Explosion is defined as a violent release of energy. Fire, we all know very well.
So thank you, Mike. So to dig into those terms a little bit deeper, I thought it was important to describe what's meant between the reactions between metal oxides, such as nickel, cobalt, aluminum, nickel, manganese, cobalt, lithium, manganese oxide, compared to phosphates, because there are fundamental differences here. So there is an escalation in terms of the reaction. If you have an initiator, let's take an internal short circuit. This is internal to the cell, and this may be caused. There's many causes, but it could be caused, for example, if during the manufacturing stage at the very beginning, to do with your raw materials, and as you process those materials to make your active material, if you introduce during the manufacturing process impurities, those impurities may lead to a compromise and end up bridging the distance or the barrier, the separator between the positive and negative electrodes. So that will, if we escalate that now, if we think about that for a moment, so you have a very local short. There will be a lot of power that will discharge through that short, which will create very localized heating. And we're talking about immediately around the location of the short. And it starts a reaction, and we call these low temperature reactions. These reactions will start to break down, degrade the negative plate, which is it's quite often carbon black or a carbon electrode, a graphite electrode. And that heat that then builds the heat within the cell that will then start to break down the electrolyte. And this breaking down, although it's not, it's a bit early for combustion, which doesn't necessarily mean fire. But as you start this reaction, you start to increase the temperature and you start to increase pressure within the cell. And so cell design has to take into consider that, particularly with industrialized products. So these low temperature reactions will then lead to increased cell temperature internally, which then consumes the electrolyte at a particular level of pressure. For example, in our product, it's around 8 atmospheres of pressure. That will be then enough to open the vent. And the whole point of these safety devices is to control this thermal runaway reaction. In oxides, it's important to bear in mind that the bonds, the covalent bonds between the metal and the oxide, so in this instance, for example, with LMO, we're talking about manganese oxide, those bonds are quite weak. And as this temperature is building up above 400 Celsius, that temperature is enough to break down the metal oxide, the manganese oxide covalent bonds, which, what does that do? Well, that releases additional oxygen that's within the cell itself that then acts as a fuel, and then that in turn increases the temperature. And once you get to about 600 Celsius for the gases, that becomes an auto-ignition level. So now the product will be on fire and will burn. If the rate of release is faster than what the cell can manage, it may lead to explosion. And these additional reactions, these high temperature reactions can lead to what we call thermite reactions, which is then at a level of temperature that will then consume the metals, even the aluminum can in instances. So the main takeaway here is that the as thermal reactions, thermal runaway occurs, it can quite quickly lead to the breakdown of the metal oxide that introduces additional fuel to increase the cell temperature. Thermal runaway in phosphates, in lithium iron phosphate, for example, is quite a lot different. The reactions are. So we start off with the same low temperature reactions, an internal short that leads to heating at the anode and starts to break down the active material. Similarly for the electrolyte, that temperature then will lead to the consumption of the electrolyte. It will turn to from a liquid to a gas. That gas will then vent in around 200 degrees Celsius. But the bond between the phosphate and the oxide, the P and the O, is much stronger, where it would take several hundreds of degrees Celsius to break down that bond. So because you don't break the bond at these lower temperatures between the phosphate and oxygen, you don't have the internal additional fuel. So you don't get the additional reactions, so you don't have the high temperature reactions, and there's no thermite reaction. So that's the main advantage of phosphate chemistry over oxide chemistries. Michael, would you like to address
sure.
number 3?
Sure. Question number 3, which lithium-ion safety standards do I have to consider? Safety standards can be divided into 3 categories related to the market you want to approach. For the US market, important standard is UL 1973, standard for batteries for use in stationary applications. For the European market, this market consists of 2 key directives. First one is defining EMC requirements, and second one is defining requirements for electrical equipment in specified voltage windows. Requirements for other markets, like for example Asia, are based on IEC 62619. And below you can see transportation and other standards which are applicable in general. And now if we take a closer look at the safety standards, UL 1973 evaluates the ability to withstand safely simulated abuse conditions. Testing is performed sequentially from cell through module to system level. As you can see, some examples of the tests, like operating temperature limits test check, overcharge, over discharge, imbalance charge, and many other tests. European directives and related listed standards specifies testing methodology for EMC and for the electronic systems below 1000 volts AC and 1500 volts DC. IEC 62619 is the standard, which is very similar to UL 1973, with slightly different test parameters and pass criteria. Below you can see other standards like UL 9540A, new becoming standard defining test methodology for evaluating thermal runaway, etc.
Thank you, Michael. So the next question, number 4, is what's the likelihood of a thermal runaway event? I can't really speak about other manufacturers, but I can put this into context for our own industrial cylindrical cells, our VL cells. So based on our return on experience and our field experience over the last nearly 20 years since we brought to market our VL designs, we're talking about frequency of thermal runaway. This is a statistical probability based on our experience of 6.1 to the minus 11 hours. So to put that into some sort of context, we're talking about at a system level, at a 480 volt cabinet level, we're talking about the possibility of single cell failing in about 323 years of continuous operation. And to kind of put that into context, if you installed your battery when this chap here, Christopher Wren, opened this place here, St Paul's Cathedral, that was in 1697, there would have been statistically a single cell event in those 323 years. It was quite difficult to figure out how to visualize that, so I hope it's at least amusing a little bit. Straight on to question number 5. What's the heat dissipation of a lithium-ion battery during normal operation and worst case? So there's really 3 stages to consider. One is during charge, one is during regular discharge, and for this example here, we've chosen our highest rate of discharge for our 2 product types, and these values are at the cell level. But we thought it would be interesting also to provide you with the values for what's released during thermal runaway. And it's not necessary to focus on the values, it's to look at the order of magnitude. So this is based on a 0.2 C5 charge rate, and these are the watt hours. For charge, it's important to know for both charge and discharge is that once you stop charging a battery or once you stop discharging the product, the reaction is finite and the heating stops. It's a little bit different when you have thermal runaway because you're obviously going beyond the capability of the cell, and now it's starting to consume, it's starting to fail. So I won't go into these values in great detail, but energy or heat rise is measured in watt hours or kilojoules. You can also convert this, if you need to BTUs or British thermal units quite easily. But to give you the scale of this, so we're looking at about 10 times the value, a little bit greater between charge and discharge, but these are over different autonomies as well. This is the watt hours released during charge. The takeaway here is that charging is really efficient. During charge, the coulombic efficiency is above 99%. So there's really no overcharge during charge. During discharge, at these, so the P is at the 5-minute rate, and the M values are shown at the 10-minute rate, and taken out to 1 hour. So you've got watt hours of energy. Again, relative to the battery system, are very low, and it ensures that you have a round trip efficiency, taking into account charge and discharge, of closer to 95% efficiency. The consequence, though, of thermal runaway, you can see that there is, and this is at the cell level, you can see that there's a significant amount of heat that is emitted by the battery or at the cell level during a thermal event. And to put the thermal event into context, our battery management system will detect a failure far quicker than any external device, such as a hydrogen detection, smoke, or fire. So once we detect through the cell voltage the drop caused by a short, for example, an internal short, we will isolate the other strings to protect them. So you have to really only account for one cell event for thermal runaway. Question number 6 is, how much ventilation do I need for my lithium-ion battery system? So this is quite clear in terms of whose responsibility it is. As the manufacturer, we have the information that has to be provided, and the different standards such as the IFC, the International Fire Code, International Building Code, as well as any local regulations, ordinances, or building insurance policies that you may need to comply with. They define what is required in terms of ventilation. Additionally, I believe NFPA 855, and which is very similar to IFC, also provides very good guidance in terms of ventilation. We'll come to that in a few more slides' time. But it's dependent on the type of battery that you're installing and the size and shape of the room that will define what type of ventilation is required. From a manufacturer's point of view, the battery may produce so little gas during a thermal event and no array to or cabinet to cabinet propagation. That's when you heat up from a starting point to adjacent cabinets to warrant ventilation. But the standards, for example, IFC will have a minimum ventilation requirement that is above and beyond what the manufacturer will suggest. The point here is that the system has to be, the ventilation system has to be designed by a qualified engineer, and the battery manufacturer isn't that type of qualified engineer. And whatever is designed in terms of ventilation has to be activated upon detection. So if it's decided that you need to ventilate after an event to exhaust any fumes, that the detection system has to act on the ventilation parameters that are defined by the qualified engineer. So we have the data as manufacturers of the characteristics of the product, the way it performs during a thermal event, which you would then take if you're designing the room or putting your battery into a room to design or consider your ventilation needs. Michael.
Question number 7. What type of fire protection do I need? Required or recommended fire protection is described with complexity in National Fire Protection Association 855 and International Fire Code 2018. Those standards define necessary ventilation, fire protection systems, smoke detectors, size and separation, and many others. It takes into account all technologies and provides the energy limits above which it becomes applicable for the certain energy storage system type, as you see in the table on the right. For example, for lithium-ion batteries installation, the limit is 20 kilowatt hours.
Okay, we have FAQ8. Now let's suppose that you've been owning and operating a VRLA battery, for example, and you're ready to make the step and take the advantage of installing a lithium-ion battery. A question that we often get asked is, do you need to install additional safety equipment? But the battery management system, as I mentioned a couple of slides ago, will be the first point of detection of a thermal runaway, of a problem with the battery. For example, it will look at the current and it will look at the voltage all the way down to the cell level. And it will take the appropriate system level actions, such as isolating the string, reporting that to the outside world, and if necessary, isolating additional strings. But let's suppose that you've got your VRLA battery, you're taking it out, but you have an existing devices such as a hydrogen detector, smoke, and maybe fire. A few comments on these is that, yeah, if you have these devices, there's absolutely no reason why you shouldn't use these as additional layers of protection. It makes every sense to do that. If a cell vents, a lithium-ion cell vents during a cell failure, then a degree of hydrogen gas will be released. In our own product, it's if a power cell fully vents, we're talking about 12 or 13 liters of hydrogen gas. So whether that would be strong enough or concentrate enough at the location of the hydrogen detector, which is usually at ceiling level for VRLA or immediately above the battery, it could be questioned because the 12, 13 liters may be diluted by that time or absorbed into the surrounding air. But the optimum location is at a higher location within the cabinet. If it's above the cabinet or fixed to the roof, then to the ceiling, then it probably won't be so effective. Regarding smoke detection, regarding conventional battery installation, that location may also be at a high level compared to the height of the room traditionally. What we experience with when we do our destruction tests, when we do the abusive tests, the thermal runaway tests, is that the smoke that's coming from the consumption, the combustion of the negative, the anode, the carbon, produces a smoke that is initially, until it's absorbed into air, that is heavier than air. So we actually see the smoke stay at the level that it's ejected at from the affected cell and module, or it will actually sink. So there's a certain advantage to have a sensor low down in the cabinet or low down on the floor, as well as higher up in the cabinet or outside of the cabinet. And lastly, regarding fire detection, because now we're talking about heat rise above the cabinet, it makes every sense if that's already on the ceiling to keep it on the ceiling. If it can be moved to inside the cabinet, then that will give you a quicker response. So those were the 8 FAQs that we decided to present to you for this first part. I'm just going to take a few slides now for Michael and I to describe certain safety aspects of the product that we bring to market that we call Flexion. So I'll have Michael just go back and touch on the safety standards that we comply with.
Which safety standards does Flexion comply with? In the table, you may see brief list of major standards, which is our product Flexion compliant with, among many others we haven't listed here in the table. As you can see, Flexion is marketed globally for US market, European market, and also we have the tests compliant with IEC 62619. So our product is UL listed and is CE marked.
So Michael, tell us what evidence do we have to show that our products are safe?
Evidence which is very easy to check in general is your listing. Pages where you can find more details are called UL product IQ, and you can search there by project number or keywords like name of the manufacturer, for example. On the picture on the right in the middle, you can see declaration of EU conformity with reference to the tested standards. On the right, you can see UN Transportation Compliance Certificate in a similar fashion as CE declaration. And compliance, for example, to NFPA 855 is based on the UL 1973 listing and test report done according to UL 9540A.
Thank you, Michael. So I just wanted to go back and talk about our particular flavor of iron phosphate. Of course, Saft can't just bring a regular iron phosphate to market. We have to have a superphosphate. And but what do we mean by superphosphate? So this purple trace here, this purple curve here, is the charge curve that I showed you on the very first slide when we talked about the lithium-ion chemistries. And we changed the our cake mixture for the positive, for the cathode, for the iron phosphate is a little bit different. And there's two main reasons for that. One is that it gives us improved power capability and an increase in energy over conventional iron phosphate without compromising the safety. And just as importantly, because we have this gradual increase in voltage, we have these plateaus, as we call them, these different stages, it allows us to really accurately balance these cell. Balancing, we mean similar state of charge, which means that we can optimize the life of the product as well as the performance of the cells as well. This is a very busy slide. I make no apologies. This is really for information for you, for the audience to take away. We'll be issuing the video. We'll make the video of this presentation available afterwards, as well as the presentation itself. So regarding how much gas does our product emit during venting? So we have two cells, and we're going to talk about the cell level. For our power cells, we have a 28 ampere hour, what we call the VL30 PFE, that's power iron phosphate. And we have a 39 ampere hour VL41 MFE. So this is optimized for discharges of say up to 6 or 7, 8 minutes perhaps. And the M's take over at about 6 or 7 minutes where we need more energy than power. So if we just have a quick focus, if we completely consume, if there's a short that leads to the low temperature reactions that leads to venting, and we vent all of the gas produced by the degradation of the anode and the electrolyte, then we're talking about a maximum of about 70 litres. Obviously, the total hydrocarbons is more than just the hydrogen gas, but as I think from the conventional battery arena, we're perhaps more familiar with hydrogen. So about 13 litres in total. If the full 70 litres is emitted in terms of the smoke and the gas mixture, we'll have about 13 litres of hydrogen in the P cells and about 18 litres in the M-type cell. Perhaps another worthwhile takeaway here is that when we vent, it's around 180 degrees, maybe up to 200 degrees, and then thermal runaway can be anywhere around 200 degrees up to about 240 degrees Celsius. That's the at the rear of the cell within the module, within the cabinet. I wanted to try and put this into some sort of, in terms of ventilation, into some sort of context. And there's very clear instructions within the International Fire Code, section 1206.2.11.3 for ventilation. It states that battery room ventilation should be designed to limit the hydrogen content, and there's other categories for other types of gases, to limit it to 1% of the total volume. And that 1% is derived from 25% of the lower flammability level, which is 4% by volume for hydrogen. But they also talk about this second bullet, which is about the minimum ventilation that shall be provided. Now, this isn't saying that it has to be forced. You might find that the qualified engineer may find that the size of the room may lead to natural ventilation that provides this minimum rate of 150 cubic feet per minute rate, or around 4 cubic meters per minute. But to put that into context for our high power 480 volt cabinet, we're talking about a minimum room size of 5.1 cubic meters, or around 180 cubic feet. And to put that into a dimensional context, we're talking about 1.5 meter room size, a minimum room size of about 1.5 meters squared by about 2.44 meters, or in imperial, in US measures, we're talking about 4 foot 9 inches square footprint. We're based on an 8-foot ceiling. So you can see that the minimum room size, if you're talking about an equipment closet, is quite small, the minimum space required. The purpose of this slide is just to put things into context in terms of performance, and really just to focus on the safety. There are other categories. This is meant to be a takeaway for you if you want to compare other values, other parameters of performance for lithium ion. Here's your cathode chemistries, and just to focus on our superphosphate. And this was put together, it's not me. I would like to claim ownership of this, but actually it was a committee of our PhDs, our experts within Saft, around 60, that created this summary of the different phosphates, or the different lithium active materials, the different cathodes. And yeah, we're not really biased here because we manufacture many of these different types of anodes and cathodes, but it's just to really draw a finite picture for LFP, that it really is considered to be safer than other industrialized products. So we're close to the end before we get to our Q&A section. So just a couple of slides to summarize that it's really my main takeaway here is that the cell chemistry, whether it's iron phosphates or whether it's oxides, it's not the only thing that you should consider, whether you're designing the system, whether you're designing the room that the battery is going into, or if you're operating and you're putting in the equipment to replace other types of batteries. But it's perhaps the most fundamental part to start at, is to consider the cell chemistry and the types of standards that it's been tested to and verified to. I can say that our own superphosphate, when you consider the system, there's no explosion, there's no fire, and there's no thermal propagation. Similarly, with the cell design and module design, if you just take the cell chemistry, then it doesn't take into account other design aspects. So with commercial grade product, typically it's mass produced and doesn't have the level of consideration because it's perhaps more price cost driven. Whereas industrial products, they're designed to take into account defects or issues and to manage those. It's not, you know, we do our best to mitigate them, but we have to have the design to manage those events. Speaking about our own product, we have this channel here. If a thermal runaway occurs and we pipe, we push the gas away from the cell to have a controlled venting, rather than, if you don't have that, then it could build up and lead to an explosion, for example, or fire. Similarly, that there are design considerations, safety considerations within the battery module, not just ours, but also other manufacturers of products. Industrial products have these considerations, and it's important that you consider that when deciding on your the type of product that you're going to install. And it's more than just the mechanical and electrical characteristics, that it's essential that you have a verified battery management system. You can have, I think it's UL 1998 and 991, which certifies and assesses the functionality of firmware and software that runs within solid state, such as within a programmable logic controller, PLC. And it's essential that you have a verified, a proven battery management system, because it's going to be your line of communication to know what's happening with the battery. And it's also going to be the brain that's going to be managing, amongst everything else, the safety aspects of the battery that you have installed. So it has to be validated and verified. And then overall, it's essential that you have a system for peace of mind, especially when it comes to safety, that you have a products, so you install products that are tested to industry accepted standards and certified, either listed or separate certification. Outside of the US, for the rest of the world, the guide is to use 62619, which is always evolving to ensure that it's covering the main aspects of safety. Also, we have 1973 that can be for our own product. We have that certified at the cell, module and system level. And then as we move into the next stage, what happens if the battery is forced into thermal runaway? How is any fire propagation managed? Does it need to be managed even? Is covered by UL 9540A. So I will just switch screens for myself internally so I can have a look at the Q&As that have come in. Let me just go here.
Well, first off, very great presentation, Nick and Michael. Thank you very much. Again, my name is Nick, and before we get into the Q&A, I just wanted to remind everybody that we did have two other webinars in our Flexion webinar series here. The first one was presented by myself, Nick Shanley, and it contained an overview of battery options for mission critical applications. Secondly, by Zenek Opachny and Ryan Bunge about integrating lithium-ion systems. And then obviously this was our third and final chapter for debunking the risks related to lithium-ion safety. So thank you again. And we still have time, so please type in your questions in the live event Q&A section inside the webinar. And with that, we can kind of open it up for questions. So the first question we had, and I'm not sure if we will have the answers, and if we don't answer your question specifically, or we don't have the answer, please contact Nick, Michael, or myself if you have, or your local staff person, and we'll try to get those questions answered specifically.
Yeah, and also, thanks. Also, any questions that we don't get to in the next 15 minutes, we will add to the package that we will issue to the attendees, so that we will answer those in that email.
Very good. So with that, let's open up the first question here. And I'm thinking maybe Michael will be the best one to answer this, but it could be something we would have to look into. But the question was, could we suggest any safety standards related to lithium metal batteries? And I believe that is for primary cells. The only one that I could think of is UL 1642, but maybe Nick or Michael, if you have any comments related to this question.
Yeah, just to give you my experience with 1642, we used to have our VL cells, the ones that I've spoken about today for Flexion. We used to use 1642 as our cell safety standard. It was tested by UL and certified by UL, listed by UL as well to 1642. Around 3 years ago, there was a change in UL's approach to cell safety, and so there's quite a clear split today between 1642 standard and 1973. UL now today, in the last few years, use 1642 for commercial grade products, for small format. I don't know if it's really for primary cells, but it is appropriate for small format, so below 10 ampere hours. And then UL guide people testing cells, if it's large format above 10 ampere hours, to comply to test to UL 1973. So for lithium metal, if it's secondary rechargeable, I would, and if it's below 10 ampere hours, I would recommend to look at testing, certifying to 1642. If it's above, if it's considered large format above 10 ampere hours, then to consider UL 1973. And if you contact UL, if you contact your local representative in your country, they'll be able to guide you quite precisely.
Very good. Thanks for that response. Second question that came in, I think this is a great question for us. As a battery manufacturer, obviously we have some knowledge with installation and commissioning of our systems. How will we be able to support end users directly in this for these services? And firstly, I think our second webinar really kind of explains this in a lot of detail. So I urge this person to go back and look at that webinar. But I'll open it up to Nick or Michael if they want to add comments. Again, this is how can Saft support end users on battery installation and commissioning services.
Yeah, Michael, if you don't mind, I can speak about this to a degree. Saft is vertically integrated, so we own everything from our raw material to produce our own active mass through to system design, manufacturing and installation. So we are today we train OEMs to install and certify those installers, but we also do installations ourselves, and we are when we ask customers that have had the system installed, if it's been done by a certified third party, when you register your installation to activate your warranty, this then puts you in direct contact with us. So if you have any questions that you can't, you struggle to get answers with through your commercial path back to the manufacturer, back to us, you can always contact us direct. And there's numbers published within the cabinet door itself, on the inside of the door, there's an email contact as well as a phone number, so you can always reach us if you have any questions regarding the operation. If you have any concerns, we're always really happy to have that feedback from the field to collect that experience.
And before Michael adds any comments, I would just like to also include that Flexion is really designed to be the drop-in battery system for VRLA battery. It's designed to work with any UPS. We as battery manufacturers, however, need to have the support of the UPS manufacturer if that's the particular application. So we always want to make sure that is also managed properly. However, as far as the product goes, it has a self-powered BMS that allows it doesn't require any kind of external power supplies. We also have designed in the IntelliConnect, which also helps us meet that retrofit application that some customers are looking to explore. Michael, any further final comments on this question?
I think all was said probably.
Okay. Let's see. And I think this was related to slide 11 or 12. So maybe just as I read this, go back into your presentation for a second, Nick.
Yeah,
and it says, where on the world are the named regulatory regulations in respect to fire protection applicable? And I believe we kind of tried to mention this in the top here as far as what US, European, and Asian markets, but mainly I could just say for the US market, when you talk about fire codes, it's always NFPA and IFC, but I don't know if IFC is for other particular markets as well.
I think the expectation is that IFC is in the process of being adopted by other states within the US and externally. I would distinguish these two sections here. This is for manufacturing the product, I would say. These standards up here, the safety standards, these tend to be relating to the installation itself. So NFPA 55 is enforceable within the US. I believe that it's being normed to expand into Canada as well. So for most of North America. And IFC, we're seeing, in fact, IFC, we are seeing now referenced even as far away as Australia. In the last couple of weeks, I've had it's cited in a lithium-ion bid document for compliance. So generally, NFPA is North America, IFC, which is very similar in its language. I think there's no surprise there. The purpose is then for it to be applicable internationally.
Very good. Yeah, and the only thing I can also add here is for this particular person, also always consider your local AHJ, the authority having jurisdiction. Talk to your local fire marshal if that's the person, and they can also help guide you to say, okay, we've adopted NFPA or we're using IFC, for example. So always check with them as well. Third question, do we have third-party certificates, and you can leave it on this slide, Nick, for EN 61000 and EN 62477? Do we have third-party certificates for those particular standards?
All these testings are done externally by third-party labs. Either it's locally, for example, in Czech Republic, or in German, France, US, Sweden for the future. But from these testing, we usually have test reports describing the methodology, the standard it covers, and criteria for testing with the pass result. So we gather these test reports, which complies to each standard separately, and then as a whole testing package together, gathered from different third-party test laboratories, we issue a declaration of conformity for European market. So it's not specifically the third-party certificate, but it's the best test report compliant with the standard which the product was tested to.
So the tests themselves were performed by third party?
In, I would say, 100% cases.
Okay, that's pretty good. So,
okay, Nick, and I think we've kind of hit all the questions. There's one additional question that I just like to comment on. It is we talked a lot about standards and some requirements for ventilation and fire protection, but and he's asking, but how about the installation standards, and what standards do you need to follow for installing the cabinets themselves? And I think the best answer for that is, again, check with the local AHJ, and they define if they're following NFPA, for example, in the US, or IFC elsewhere, or combination of both. So always check there first, and then inside those standards or recommendations, because NFPA is more of a recommended practice. From there, you can kind of see what are the details as far as installation goes. But again, any final questions before we wrap up? Please type them in. We have a few minutes left here. But Nick or Michael, any closing remarks that you like to make?
I think it's clear that as we build these, as we get the market information back, as we get these questions and we build our library of FAQs, we would expect to have an update to this. In other words, bring, say, the next 10 or so FAQs in a similar seminar. I've really enjoyed this. I hope the audience has as well. I hope you found it informative. This is just the first one that maybe in the new year we'll be ready to have a second one to address the next level of questions.
Very good. Michael?
I would like to thank all the participants that they joined today and listen to what we were glad to present. And I think we enjoyed, as Nick indicated. I think that's all. Thank you.
Yes, very good. Thank you, guys. And again, if you need a copy of this presentation, please contact your local your Saft representative, and we'll get this presentation to you. And with that, we can close out our third webinar. Thank you, guys.
Thank you very much, everybody. Take care. Bye-bye.
Thank you all. Goodbye.